what I'm going to discuss today is indeed the Hyper-Kamiokande experiment, and I will start with first a description on neutrinos, because this is a neutrino experiment. So what we want to do is to first understand what neutrinos are. Then we are going to move on to an overview of the experiment, what the physics performance is, and then the current status and perspectives. So first, I will give a general introduction about the neutrinos. So neutrinos are very important. And neutrinos is something that is all around us. So it's, this is why it's important to understand them, but also they are important because they drive some physics phenomena. And there are neutrinos, there are billions of neutrinos coming from the sun. You can't see them, but they are here. The same from the Big Bang or many other sources. So we have these neutrinos everywhere. And neutrinos are part of the elementary particles. So this is just the description, really, the indication of which the elementary particles are. So we are starting with the quarks, and then there are the leptons, so-called leptons, out of which neutrinos are the counterparts of so-called charged particle leptons, like the electrons that you may already know, muon, taus. And then we have the first carriers, to which we should add as well gravitons for the gravity. We don't know that. There will be something called graviton, and then also the Higgs boson that was recently discovered in 2022. But what we are going to focus on are really these particles, the elementary particles, electron, muon, and tau neutrinos. So I mentioned that it's very hard to have a neutrino interaction. It's very hard to observe neutrinos, which means it's very hard to have them interacting with something that is that allows us to detect those ones. This is not the same for instance, quarks. In all these experiments, like at CERN, we observed lots of events. And the reason for that, and here we are just describing the type of interaction. So the reason is indeed the type of interaction. So we have the quarks. So again, elementary particles. There are different ways in which there is a quark interaction through gluons, weak bosons, but especially gluons. Charged particles, so the counterparts of the neutrinos. And neutrino exchange goes through weak bosons, and as the name says as well, it's already something weak, something that will be hard for us to detect. But it's not just we want to know, we are curious to know about our environment, but also in this case there is a motivation for that, it's based on the matter-antimatter symmetry we see in the universe. So what we see is matter. We don't see really antimatter. There may be pockets of antimatters, but really we see matter. And this was different at the Big Bang. We postulated that at the Big Bang, the universe had the same number of particles and antiparticles. They annihilated, but there was, in some ways, more matter than antimatter in some process that eventually brought us to have a world of matter. So this is the current universe. We observe matter. And the mechanism through which we can observe, obtain from an original world of matter-antimatter could rely on neutrinos. So the mechanism that indicates the matter-antimatter violation is called the CP asymmetry, and we'll hear this word, the CP, in the future as well in these slides. But this violation, so the fact that we don't have an asymmetry matter-antimatter, was originally discovered in quark, but it's not enough. So we assume that neutrinos may be our best tool to understand why matter exists. Neutrinos, though, I mentioned, they interact weakly, so we can't easily detect them, but also that means not just that the boson is weak. What it means is that we need to have, to detect those ones, quite a lot of matter. So we need to have quite a lot of physical interaction before we observe neutrinos. So and generally then we need to wait, we need to have the big detectors. This is why they are big detector or very dense, something that will allow us to observe neutrinos. And this is different from other particles like alpha, beta particles, etc. The other characteristics of a neutrino is that they are almost massless. They were postulated to be massless. So the standard model particle physics originally said, oh, they don't have mass. This is not true. The evidence through neutrino oscillations that we will see in a moment indicates that they have a mass. Out of 3, 2 must have a mass. So, so we are at the point that we very hardly managed to stop these neutrinos, to detect those ones, and we know they have a very small mass. How small it is, here you can see the order of magnitude, GV for the, for instance, for the quarks, leptons, and charged leptons, and these we are talking about MeV, so it's much smaller or less. We are talking about something, less than electron volts. So we are talking about many order of magnitudes, no order of magnitudes, so difference that we need to address. It's not the topic of this talk, but we need to address why the matter is so different. So neutrino oscillation is a major part of really neutrinos and the way in which we can detect those ones and the way in which these experiments are built. So neutrinos, the oscillations of neutrinos obey quantum mechanical phenomena. So a neutrino is a particle in the wave, and what happens is that they, when they propagate in space, they oscillate between neutrinos and antineutrinos. Actually, we'll see the mathematical formulation. They are a mix of mass eigenstates. So what it means is that if we start, for instance, from muon neutrinos, they propagate as neutrino 1 and neutrino 2. And eventually, when we detect them again, so we produce them in a flavor, so-called flavor, they propagate, and then we detect them again, and then these has the probability of being one of the other neutrinos, and for instance, it becomes an electron neutrinos. So this is not a generic representation only, this is really what happens. We start with muon neutrinos in our experiment, and then what happens is when we detect them, so further away, after almost 300 kilometers, we detect them, and they are electron neutrinos. But now let's go more in the math of our representations. So flavor eigenstates is electron, muon, and tau, so neutrino, electron, muon, and tau. And these are a superposition through the mixing matrix, that is the PMNS Punte-Corbon-Nakagawa-Sakata matrix of the mass eigenstate. And if you're working in B physics, that's exactly the same as the CKM matrix. The values are different, something that is a mystery, we need to understand that, but that's the same process. And this is a 3x3 unitarity matrix, so we are dealing with 3 real parameters that are indicated by these theta, these angles, theta 1, 2, 1, 3, and 2, 3. And then we have an imaginary phase that is called delta Cp. And this goes back to what I was mentioning before, that is what we want to measure. The moment that then you want, we looked before that we start with a flavor and then we may end up in a different flavor with a given probability. So the oscillation probability to move from alpha to beta, or muon to electron, is represented using the expansion of this equation by this equation here, that depends on the matrix elements of this matrix. Now, there are a few things to note, is that we need to have a representation of these matrix. There are different, the one adopted here is the product of 3 different rotational matrices, and you can see that just in one of them there is the Cp factor. There could be others, but we can also have an invariant representation that indicates actually that what we measure, the Cp violation, is proportional to that, is equal to that. So what we measure is independent of the parameterization. And then this representation that depends on the parameters, it depends also on other parameters, not just from the use, it depends on the L, it depends on, that is the distance between when we start with the neutrino and when we detect that. And then it depends as well on the energy of the initial neutrinos And it depends as well on the delta m square mass, which is the difference of the masses squared. Now let's look at the expansion of this formula. We can see that there is a dependence in this term, plus or minus, on the type of neutrinos you have. So this probability as a minus for neutrino and plus for antineutrino this term. So this means that when you are measuring the CP, the number of neutrinos in the detector where you detect them after they have been somehow generated and have propagated, in that case it depends on whether you are starting with neutrino or antineutrinos. Then in that case you will you have a different factor, and then you will see that the probability is different, so then we can measure CP violation. So CP violation happens just if neutrino and antineutrinos, when they propagate in different way. And just to know that this is a propagation from a muon to an electron. If it was just muon or electron will not have that. Right, so the other parameters that describe the neutrinos are really the masses. So the mass eigenstates 1, 2, 3 that we have introduced before, and that is the way in which the neutrinos propagate, they, we can write them through the same mathematical formulation we introduced before, and they depend then on the neutrino electron muon and tau with a different percentage. So we can see that they are composition of with different values of these flavor masses. But then the other characteristics is that this delta m square introduced before, when I introduced the formula for the oscillation, the delta mass square, if we just look at the oscillation per se in vacuum, we'll not be able to determine the sign of this delta m square. So we don't know whether m1 is greater than m2 or vice versa, just looking at the vacuum probability. If we instead use the matter, we have a crossing through matter, then we will be able to determine whether the sign is positive or negative. However, what happened so far is just delta m square 1, 2, that is related to the neutrino coming from the sun. Just that was determined, the sign, but not delta m square 1, 2 that we want to determine in our experiment. So what happens is that you have an ambiguity. You have either neutrino 1, 2, and 3, or neutrino 3, 1, and 2. So this is called norma, just 1, 2, 3, or inverted 3, 2, 1, 2 hierarchy. And we want to measure that. We want to measure what the order is. But for doing that, we need matter. Now, I mentioned ideally what we have, our landscape, but it's not a sort of a totally green field. We have been studying that for many years. And we have here just a complex fit. We're not going to look at the numbers, but you can see that there are these parameters that have been determined. These are the sine and the corresponding values of theta. Or you can look at the corresponding U matrix or a corresponding representation, graphical representation. But these are not all known. What we still miss is the value of delta Cp, that's related to matter antimatter, the mass ordering, what I mentioned before, that we need to determine that through our own oscillations, whether it's plus or minus. And whether, and the other one is this angle theta 2, 3, that we don't know exactly whether it's maximum, that means 45 degrees or not. So we want to determine that value as well. And in order to do that, we need to have experiments that are focusing in particular on these values. Now, there are many neutrino sources. So moving on more on the experimental part, the results, there are many experimental and many neutrino sources. Now, when they are natural neutrino sources like atmospheric, supernova, solar neutrinos, etc., all these ones, we don't have really a handle in choosing really the length or the energy, etc. What we can do is that when we create those ones, when we created the reactions, for instance, through accelerator neutrinos, so that means we generate those ones, we can have a handle on the energy and the length of those particles. But in general, you can see also there is a very wide energy range. many order of magnitudes. So neutrino observation, I just mentioned, that came through reactor neutrinos. So they're coming from the reactor interactions, nuclear interactions. We have a flux of neutrinos, so that were observed for the first time. And actually, neutrinos are a way to monitor whether there are nuclear interactions in somewhere. So there are also neutrino detectors used for monitoring nuclear reactions. Then the observation came through natural sources, atmospheric and solar neutrinos. And then we got the current experiments. They want to determine, using different beams, the parameters. And those are accelerator neutrinos, the ones muon into electron neutrinos, the atmospheric neutrinos, so the ones that are coming from the cosmos, I mean those are cosmics, solar neutrinos and the reactor neutrinos. In our case, we'll not use reactor neutrinos, just the other three. Then we have astrophysics, so we can use neutrinos coming from the neutrino burst to determine the property or what the models are, how we had, for instance, a neutrino burst, supernova burst. And then also we can measure extragalactic cosmics or galactic cosmics to understand more about really the cosmics, what happens and how they've been generated, etc. So these are the ones we are going to focus at the moment, but then we look as well at astrophysical neutrinos. So, Kamiokande, so Hyper-Kamiokande is the third of a generation of Kamiokande detectors. So first we started 30 years ago with Kamiokande. This actually was a detector for measuring proton decays. That is another thing. That is something somehow that hasn't been measured yet, something beyond the standard model, beyond what we know. But that was the original reasons. But then what happened was that it was much more successful, observed together with other experiments, the supernova. So it was the origin of the birth of supernova astrophysics. We had Super-Kamiokande. Then a few years later, due to the success of Hyper-Kamiokande, it was built a detector that was 20 times larger. And in that case, instead, we discovered neutrino oscillation. Again, there was a counterpart with the solar neutrinos. These came through atmospheric neutrinos, but together with a so-called experiment, SNOW measured the oscillations. And finally, we have Hyper-Kamiokande that is 8.4 times larger than the Super-Kamiokande, and it has really a huge mass. Now, this is a more complex detector because this has this experiment is not just the far detector, so the one that detects the neutrino, is also the one that produces the neutrino. So we have the accelerator here that is at J-PARC on the other side of Japan. This is Japan. This is north of Tokyo, and then on the other, so from Tokyo towards China, Korea, you shoot the neutrino beam and the Kamiokande, you detect that. And then here you have the generator, the beam, accelerator, and then there are also the so-called near detectors here. And the near detectors, what they do is to detect, they give you a snapshot of the neutrinos at that point. And they are important because this snapshot is important to reduce systematics related to the neutrinos and to the beam. So a little bit more about this neutrino, how do we produce the neutrino? Neutrinos are coming from a protosynchrotron, so they are protons. They hit a target, they produce pions after the interactions, and the pions decay with neutrinos, muon neutrinos. And these muon neutrinos then are the ones that propagate through Japan. So we detect them here, we detect the near detector, far detector, and these are neutrinos. We have a little off-axis. So the direction of neutrinos would be this one, but then they are 2.5 tilted, the ones we detect as Super-Kamiokande, because due to the pion kinematics, decay kinematics, what happens is that those at 2.5 degrees here, they are much narrower, so that means you get rid of this part, which is in most cases just background. So that's a good thing. It's not just reducing events, it's just reducing what will make difficult to find the neutrinos. And then here I just want to highlight this is the probability, the P muon into electron neutrinos, so the probability of oscillation as a function of the energy. And if you just, these different values, they are given for different values of delta, and the two different solid and dashed line indicate the normal inverted hierarchy. I just want to highlight that if delta, for instance, is -1/2 pi, you will have this comparison between the flux of neutrino and antineutrinos of the probability oscillation that has 25% difference. So what happens in that case, we have a big difference between neutrinos and antineutrinos. Now, I'll mention a few more words about atmospheric neutrinos. So these are coming from cosmics. They interact with the atmosphere, they generate neutrinos through the different interactions, and depending on where they are detected, say in Super-Kamiokande or Hyper-Kamiokande, they can come from any parts of the globe, and depending on where they come from, they interact, they cross different parts of Earth, so they have a different matter interaction length. Now, if we look at the angle, the zenith angle, and we plot this one, actually the cosine, versus the energy of the neutrinos. These are neutrinos coming from the cosmic, so the cosmic, you know, it has a wide spectrum, so neutrinos will have a wide spectrum. If you plot that one, we can see that for the probability for neutrino and antineutrinos is quite different. There is an effect due to the matter, to the interaction with Earth, and this will give us will allow us to distinguish between between neutrino and antineutrinos. So again, will allow us to determine CP violation. But again, will also, if you compare this one with inverted hierarchy ordering, in that case as well, we'll be able to determine the sign, the ordering. So in the case of atmospherics, actually there are two effects. We can determine CP violation as here, or we can determine due to the matter effect the ordering. And just to mention that this plot would be the same, would be inverted in the case of the antineutrinos. So so it's important we have the beam, as we have indicated, but also the atmospherics, because although we don't know what the matter hierarchy is or matter ordering, we can use the atmospherics to give this information. And here you can see, for instance, the sensitivity to mass ordering using a beam of neutrino and antineutrinos, and you can see that we get for different values of the parameter theta to 3. I said that it's 45 degrees plus an error, so we don't know exactly what it is, and we can change that value just to see how the determination of mass hierarchy would change, and we can go from 3.8 to almost 4 to 6 sigma of determining this mass ordering using beam and atmospheric neutrinos. And this you can see here, this is the probability as a function of the running time of Hyper-K. So this is for 10 years. So we are assuming that Hyper-K runs 10 years. It's not totally true. We assume at least 10 years, 20. And here you can see for the beam we assume that we run 1/3 with neutrino beam and 2/3 with antineutrino beams. So what's happening is that you get more a beam of neutrinos than antineutrinos because of interaction regions. You get you get more somehow events for neutrinos, but this is something that we'll determine in the future. And then similarly, so you can get the mass ordering using our events, and we can get as well the sensitivity to the angle theta to 3 that we said, and in this case again using atmospheric beam that you can see in this plot. After 10 years we get for a value of sine square theta to 3 about 6 sigma of knowing the octant of theta to 3. and these plots, they always show the rejection of the opposite, the option opposite to the one assumed, versus the number of years of running. And in this case, instead, we focus on the CP violation. So first there are the two parameters, and then a CP violation. This again is for the two opposite cases of the mass ordering. This is a normal ordering, this is inverted ordering. Again, this is the value of a true value of delta CP, and we can get about, at 5 sigma, about 50, 55, 60% of the phase space we can detect, larger 70, 80% in case of 3 sigma. And the use of atmospherics, though, make sure that the combined beam of neutrinos and atmospherics compensate the lack of knowledge of mass ordering. So this is what I said. We use the atmospherics because they have a more, give us a handle on the mass ordering knowledge. Now I change flux, so that was important. Those mixing parameters have been determined using, or we aim to determine using the atmospherics and the beam neutrinos. Now there are other parameters, and we can determine them using the solar neutrinos. So those are neutrinos coming from the sun, and they are coming from the PP reactions generally. So you have a PP1, PP2, etc. And you can you obtain a set of neutrinos. They are escaping the sun, they are carrying energy, and they come from different reactions. So here you can see, for instance, the flux coming from the sun as a function of the neutrino energy, because these neutrinos will have a different energy. And an experiment that would measure these these neutrinos will be able also to somehow reflect on which the reactions were in the sun. But then there are two things I like to highlight in the case of neutrinos. So neutrinos, they have a so this is the probability of neutrinos oscillating as a function of the energy. And there is first the vacuum-dominated oscillations, and then at the end we have the matter-dominated oscillations for higher energy neutrinos. And in the middle we have, so this is really energy dependent, and in the middle we have the so-called upturn. So what we want to measure, because you can see here that there aren't many dots that represented the data, what we want to measure is neutrinos in this area. And this is called the upturn sensitivity, and this again is the sensitivity to discover the upturn, so to measure neutrinos in this area, and for different thresholds we can get a 3 or 5 sigma discovery potential. Again, this is about 10 years all the times, but we assume to run much longer. Solar neutrinos as well, if you look at the plot again of delta m squared this time, so in the case of neutrinos it's delta m squared 1, 2, and sin squared 1, 2 again. In this case, if we look at the corresponding contour coming from solar neutrinos, they are the ones in green. But we can measure as well these parameters using the reactor neutrino. And in this case, you can see that the mean values are different of about 2.5 sigma. So in this case, what happens is that there is some disagreement. We want to understand why there is disagreement. One possibility is to have the daylight asymmetry measured by Super-Kamiokande. And does require time, of course, but still we will be able to reach in 10 years 5 sigma observation. Then we have also other neutrino sources. So let's look at what happens in the case we move to astrophysical neutrinos. We already discussed the solar neutrinos, which are astrophysical neutrinos anyway. But let's look at the supernova neutrino, supernova burst. So supernova neutrino come from are at the end of the long process in a star that eventually, depending on the mass of the stars, may produce a supernova burst. So from the supernova burst, you may have neutrinos coming actually from the silicon burning a few hours, 8, 10 before the actual explosion that we observe on Earth, and then we have a neutrino burst. So the neutrinos coming all together from the explosion of a supernova. But there are many. They are not just a few. They are not the same 10 or 20 or even thousands. We are really talking about a large number. This is a 10 at 9 of neutrinos. So they are coming in a short burst from the supernova. And so these need to be determined. So there are many challenges. These neutrinos, though, they arrive on Earth, but depending on the distance of the supernova, they change the rate that we will observe less neutrinos. The closest ones, so Betelgeuse is the closest one, we'll observe 10 at 9 or 10 at 8, and then we still expect thousands of events coming from, for instance, the galactic center supernova, or Andromeda, 780 kiloparsec, so 10 events. So we have the ability to measure these neutrinos at Hyper-Kamiokande, and these are, it's very hard to really monitor that, to really detect that, to make sure that we don't have any downtime, and we always detect those ones. Regarding supernova bursts as well, it's very difficult because there aren't many events, there aren't many cases in which we can say, well, okay, we have a supernova burst, we have a model that represents that can be for neutrinos, we can have a model, but what about supernovas? We really don't observe those ones. So there are many supernova models, there are many simulations for the supernova bursts, etc. And we started to look at the different distributions for different values, for different types of modeling. So what happens, for instance, this is the event rate versus time, etc. So this means that not only we need to detect neutrinos, but we need to identify them as much as possible. Say the pointing, so where they're coming from, the energy resolution, in order to help as much as we can addressing what the modeling is, how this process, really understanding the process in the supernova. I'll mention a couple more things. So we may look also at pre-supernova burst. At the moment, this is an example from Super-K. So this is an alarm. So you can determine neutrinos before they arrive. So you're ready. Oh, they're coming. And this may happen in the other experiment, Super-K, which is before Hyper-K. It may be easier because now there is the ability to detect neutron in this interaction, so it's easier to detect this interaction. It may be more complicated for Hyper-K, but this is a possibility which I found very interesting. Still about supernova, it's not all. Supernova have been exploding in our galaxy since ever, really. So what we call that the diffuse supernova neutrino background. So the ones, they are the neutrino coming from the past supernova, or we call them in Super-K, really, supernova relic neutrinos, but they are the same. So we can determine those ones, and I just want to highlight this plot that shows the number of events versus the energy, and we have, though, a very large background here that we want to remove, because we don't really have many events. These are 40, for instance, so we are trying to remove as much possible the background, and we are ending up with a handful of events, and we aim to determine those ones. So last but not least, just before giving a description of the experiment, the proton decay I mentioned before. For Super-Kamiokande, the proton decay is what we want to measure for Kamiokande, but then we got so much more physics to address. So the proton decay in this case is a phenomenon has never been observed. these may also have implications beyond the standard model. For instance, this is the favored decay of a proton in 20 neutrino kton plus from the supersymmetric models. We also have the flagship for Hyper-K, that would be the proton into electron plus pi 0. But we have also many other decays in mesons, leptonic Fana states, etc. And but we'll be able to reach a very high precision. We'll be able to say explore a lifetime of the order of 10⁻35 years. So we'll manage to try to address this issue. So just a summary of the physics. This is a multi-purpose experiment. This is sensitive, Hyper-K, to different neutrino physics, and it has a wide range of energies that it spans. But now, just the last part, I'll just say a few words about the status of the experiment. So the timeline is that we are not running yet. We are starting to run fairly soon in 2027, but before that there are about 3 years when we are building the experiment. So the cavern, that means these experiments are all under a mountain. Super-K is under 1 kilometer really, so that is 1,000 meters. In the case of Hyper-K, it's a close by mountain and it's about 650 meters. Overburden. So first of all we need to excavate that, and we will see a few plots. Then we need to produce whatever is needed to detect these neutrinos, to detect the light coming from the interaction of neutrinos with the water. And then at the same time then we'll have to fill the tank with water. That takes 6 months. On the other side of Japan, I mentioned we have an accelerator. These as well as half of those near detectors that already exist. But now we are dedicating to upgrade these accelerator, higher beam power, more near detectors, and finally we'll arrive at the start of data taking in 2027. So here I just have a few pictures now to indicate where we are. So this is a mountain under which the Hyper-Kamiokande experiment will be built or is being built. So you can see there is actually, we are not going down a mountain like happens in other experiments. We are going parallel. So we have the mountain and we are going down. So for us it's just somehow a tunnel. And these tunnels have been excavated already, and now we are at the top of this tank. And this tank is progressing from the top to the bottom, and you can see this is the top. The top has been already built, and we are close to have reached the full size of the cylinder. So that is 69 meters of the dome, and then we'll go down. And this is where we have water. We need to put the water in the tank. So this is they will contain water, the water system. A few more words about the last few minutes about the detector. So the detector, this is full of water. We'll say why in a moment. And this detector has a frame. This one here. This frame has so-called PMTs, photodetectors, on internally looking towards the inside, and this inside is called an inner detector. So this is where the physics interactions happen, in the inner detector. Then we have the outer detector that has a outer role where we have other PMTs, a bit smaller, and those are needed to reject what happens from the outside to the inside. We want to reduce the background we have there. So-called background. So we want to make sure that there isn't anything that mimics our events. So then what happens? The interaction I indicated before is the main interaction we use. So we have this weak interaction. We have a change from electron, or muon neutrinos to leptons, so the corresponding electron muon neutrinos. This is the standard CCQ interaction. And then we have the interaction, of course, with the atom. Why do we want to have a water Cherenkov detector? I mean water, because it's a water Cherenkov detector. So from the interaction of neutrinos, we have a muon and electron, and then this will produce a Cherenkov light. So what we will see in real life is a ring of light. And we need those PMTs to detect that light. So this is why we have all those photosensors that they convert the light into electricity, really, electric signal. And these need to be all clustered around the detector in order to see this ring. Why do we need to see the ring? Because depending on the shape of the ring, we understand whether they are muon or electron neutrinos. And this is, for instance, for a muon neutrino. And this, what you can see, is the opening of the cylinder. So these two are the lids of the cylinder, and this is just the body. And so we have the electron neutrinos, which sharper in the case of the muon neutrinos, and this is, for instance, the case which we have a pi 0 into 2 gammas, and which is a background. Not giving much details about that, but you can guess that this is a bit fuzzy, this is a bit large, and this, if they are close enough, they can mimic the they can mimic the signal here. But the good thing for electron neutrinos is that, for the water Cherenkov detector, it has a very good separation between muon and electrons. Just a couple more words. This tank I indicated before, this is the inner part, and behind is the outer part, has these big PMTs. They are encapsulated in this shell, in this capsule cover, to avoid that if this one for some reason explodes due to the pressure, then it creates a chain reaction. We have the electronics in water. This is very important because we need to be sure that the electronics doesn't fail. You can't go there and replace that. We have what I mentioned, the outer detector. It has much smaller PMTs that detect the light coming from the outside, or perhaps if there are signal expanding there. And multi-PMTs, there are different category really of these big PMTs, just with 19 of these small ones. So, and then the status. We are progressing, as I mentioned. They have arrived since actually was a sort of nice Christmas present, December 2020 or something, in the middle of the pandemic, but they started to arrive. Yeah, and then they're being assessed. So we have 20,000 of these guys here. These ones are being built, multi-PMTs, as well as the outer detector. The electronics, just to mention that this is very challenging because it can't break. That's really the most crucial part. You need to have something that doesn't break in the detector. 10, but really ideally 20 years without changing anything. So that has to be really space graded. So when you have something in the space, you don't want to change it because you can't. Similarly, for what happens in Hyper-Kamiokande. So it's very crucial then for us the testing of the vessel, the testing of the electronics there. And then the last bit before concluding, the near detectors. So these are the ones I mentioned before. They are needed because you want to take a snapshot of the beam before it propagates, so before oscillates. And we have a near detector that comes that is already there because, as I mentioned, we have a T2K and we have a Super-K, and the corresponding experiment is T2K with a beam. These two detectors on axis, so 0 degrees and 2.5 degrees of axis, are there already. They are being refurbished. So for upper K, we should get the ones. I mean, we will get the ones refurbished now, and then we'll refurbish them in the future. But for now, we'll get what we have at the moment, what we'll have at the end of the year. Why they are important? They're important because here we have a magnet. So the interaction of neutrinos with whatever the detector here is, the fine-grained detector or the super FGD, etc. So we don't care now to describe what kind of detectors are, but what happens is that we have an interaction here and we have a magnet, so we'll be able to describe what kind of interaction we have there. And the other thing is also we have a new detector. This time is called the intermediate Cherenkov detector because it's a little bit further, not as 280 meters from where we produce the neutrinos, 900 meters, and in that case we have water. So we'll be able to detect something that has the same target as the far detector. And there is also a novelty here. We have a small detector here of the order 8 and 6 meters cylinder that goes up and down, spanning 1.4 degrees around the beam, and the issue is that, as we have seen, depending on the off-axis angles, you have a different beam. You are able to observe a different flux, and using this information, we'll be able to again to minimize the systematics because we can understand the different types of interactions. And now we are at the end. So Hyper-Kamiokande is a next generation neutrino detector, a generation neutrino detector. It aims to measure CP violation, that's crucial, but it has a very wide physics range. So other parameters in the PMNS matrix, but also astrophysical neutrinos. The experiment is currently being built. We aim to take data in 2027, and it's really an exciting time to work in the experiment. Thank you.
Thank you so much for the nice talk. This may be a very naive question because I'm a theoretical physicist. What was the reason that Japan was chosen for this experiment? With a lot of seismic activities, I would have thought it would be a pond rather than a probe. Is it just...
So the part of Japan, say where Hyper-Kamiokande, where the experiment, the far detector is not so much seismic. The real seismic part is where you have the accelerator. So that's actually it happened when we had the problem. But that is, even if you have a small seismic movements, they don't affect much the neutrino. We don't have major issues at the moment due to that. The only exception was when there was the big earthquake in 2011. But that was a magnitude 7, very huge, and that meant a downtime of 1 year. But going back to your question is that Hyper-Kamiokande comes from, the far detector for supernova, etc., was built there starting from the small experiment, and that is not very much seismic. But the other one, the accelerator, was already there for, per se, for life science. And then there was the idea to say, well, okay, we have the far detector, let's then have a beam going to decay. So in some ways it came generating on itself. It wasn't like starting from zero, we start to build it. Yeah.
May I ask another silly question?
Just to add into that to the rest of you, that the accelerator is of course the same accelerator that will be used for the Comet experiment that we have an involvement in here. So they're actually sharing the same proton accelerator.
Exactly.
Let's take the question over here and I'll get back to you. Alex?
Yeah, so the two ordering schemes for the delta and 3-1 squared, is there any early indication over which one is preferred, or is there just no prediction?
Yes and no, meaning that different experiments may have different preference, and at the moment it seems more normal hierarchy, but there are a little bit different indications between the experiment in Japan and actually the one in the US. So, so at the moment, according to me, it seems the higher. Seems more normal ordering, but we can't say anything because we have two different experiments at the moment. Yeah.
You're right first, then back to Amos.
Thanks for the great talk. I was wondering if you could put back up the plots for showing atmospheric neutrino properties with cosine secant angle on the vertical axis. I had a question about what are the features in the plot.
Yeah.
Yes. It looks like there's a discontinuity in cosine zenith angle at around negative 0.85, where
Yeah.
there's a sudden skip up that line. I was wondering if what's responsible for that.
So we have a different. So we have a detector that we have that is the cylinder. So I'm not sure, but it could be this is in the experiment. So could be really we have a cylinder. So you are moving in different regions.
I thought maybe it was the geo.
Could be a transition from light from the bottom of the cylinder to the side.
Okay, I thought it was more maybe deeper, having to do with the makeup of the Earth's composition or something. But
this is also for the experiment as well. So yeah. No, I don't have the plot for the Earth. Yeah.
So, when you were talking about warding off background effects in Hyper-K, you mentioned that you have a row of photomultipliers again, which is a bit. I don't understand the reasoning because I assume photomultipliers would be there to enhance the signal.
Oh, so actually they have two. So,
about the role of the outer.
and I understand that. I just want to get the plot once I get it. Right. So what happens is that you may have some radiation coming from the rock. So this is rock. So you may have, I don't know, for instance, some photons or something. So you want to make sure that you detect when you have the background coming here.
Oh, so it's to detect the background.
Yes, yeah. Or you may have spallation muons coming from the outside. So you want to detect whatever comes from the inside to the inner detector. I mean, you don't want to have some events that appear there and then cross into here, because here they will be detected. Yeah. So you want to remove anything that comes from the outside. Yeah. They also use actually also for Cygna, because when you have, for instance, very energetic muons, cosmics, they cross and they arrive up to, they may not be contained in the detector, they may go also out of the detector. So they may also have help for Cygna. But they're, for instance, for beam neutrinos, they are mainly used to reject anything that may come from the outside. And we use that. This is similar to what happens in T2K. I mean, when the first indication of CP violation we have from the T2K experiment, that helped to understand really it was a signal, because we had a lot of events, statistic reasons, towards the wall, towards this part, and then that helped to understand that. But yeah, you just don't want to have anything coming from the outside to the inside.
Two questions, both not particularly technical. Is there some sort of assessment about the environmental impact of building such a large experiment and hollowing out a mountain and so on? Like, what are the environmental consequences of doing such a thing? Is there some sort of strategy in place to mitigate that, or is it just?
So the detector per se, this one has minimal implication. It's just the recycle of the water, so one tries to minimize that, and we have quite a lot of interactions with the local community in order to make sure that there isn't really any leak, you don't get things outside, etc. So for the fire detector, there's quite a lot of interaction with the local community. For the near detector as well, we do have interactions, but just to mention about the beam, and that's the main culprit really, is always the beam, the accelerator. And in that case, there are initiatives. I can't mention exactly the details, but there is initiatives to try to minimize the impact on the environment, especially in the construction. But yeah, there is work in that direction, but being an accelerator as well needs to compromise the use of resources. Yeah. And then there was another. Oh no, sorry, you had two questions. No.
Maybe take one from Yuki.
So in some slide you show that there's two types of different photomultiplier tubes. One is multi-photomultiplier and the other is larger one. Are there any specific reasons?
So this is fairly similar to what you have in, say, KM3net. So the original, the idea was the people working on that who proposed that indeed are people coming from KM3net. And the intention is to have more PMTs, so you have a more signal in that in these 50 centimeters, so more points, so you may improve your vertexing. So that was the, I mean, these two, this one and this one have the same size. They are different technologies because in this case you have the electronics inside, in this case you have the electronics inside in the boxes. But they have the same say dimensions, and yeah, and this actually is fairly precise. I mean, quite nice timing resolution, and so the intention is to be more precise. Effectively, at the end, they are mainly used really for calibration. At the end, we have done studies, and they are mainly used for calibration, not only. So we need, I think at the moment I wrote about 1,000, but it's about 800 that will be built. Some of them may or may not, so we are still discussing that, and LED for calibration purposes. So they are there, they're helping originally because they want to be much more precise, and now they are precise, more precise, and they are used for calibration.